So our speaker today is Dr. David Gagne. He's a machine learning scientist at the National Center for Atmospheric Research in the US, and he's going to talk to us about some of the latest developments in machine learning for weather forecasting. So, David.
Thank you, Donald. I really appreciate the invitation. I'm excited to speak to you all today. So I'll be talking about our new credit system, which is the Community Research Earth Digital Intelligence Twin. We've been developing this for the past year or so, and kind of the motivation for this came after sort of following the rapid expansion in performance of these AI weather prediction models. You've seen with a lot of exciting nature and science papers for things like GraphCast and Pengu Weather and ForecastNet and whatnot is that we went from basically models that were performing kind of pretty well but not as good as the IFS to models that were able to outperform basically the ECMWF IFS model. Since kind of the initial flurry of major papers that come out, quite a few other groups have also developed their own systems or running their own systems with different variations and different architectures. But at the same time, a lot of we're not really seeing a consistent increase in performance anymore. We're also seeing some kind of more experimental architectures. We're basically training models from trying to train models purely from observations, but those so far are not performing as well as the ones based off of reanalysis. With these good skill scores, that one thing we are seeing with this is that just because you have a good skill score doesn't necessarily mean the model performs well in all aspects of how one would expect a model to perform. And so there's a recent paper by Slavinsky et al. That is running cycle data assimilation using various AI NWP models as kind of the background state. And what they were finding was that all of the models would go unstable at one point or another, except for the neural GCM stochastic model. And that's all these suns is basically where the models blow up. And then the neural GCM stochastic, while it performs, it doesn't go unstable. It performs worse than the GFS model, run at 1 degree. So this leads us to think that there's a lot of other things about the system. It's not just about picking necessarily a big architecture, but that there's other properties of these AI modeling frameworks that go back into the pre-processing decisions and what physical constraints you apply to them that matter and that need to be explored much further. And so what my group and the broader credit team have developed is what we're calling the credit, or as I mentioned, the Community Research Earth Digital Intelligence Twin. The idea behind it is to have an open foundational platform for developing and deploying AI weather and Earth system prediction models. And where we're trying to add value over other systems is that we're not just focusing on basically one data set or one modeling framework, but we're making the system very customizable so that you can plug in different data sets, try different model architectures, and add physics to the process through initially kind of conservation approaches, but we're open to expanding further. And since it's research focused, we basically flexibility and customizability is a key part of this process. So some of our value propositions, unlike groups that, while we have a good sized supercomputer in NCAR, we are still interested in minimizing latency and minimizing our training costs. So we've been going for trying to make the models as fast as possible while still being competitive with other AI NWP systems. And we've been able to get our time stepping down to about 0.75 seconds per time step, which is, as far as I can tell, the fastest of the models that are doing better than the IFS. We also reduced our dependency, so it's relatively easy to install basically on different computing systems. Again, the platform is very flexible. We want to support just about any kind of AI model, and be able to configure a whole pipeline in a single file and run it on just about any kind of computing system that you can install PyTorch on. I also try to we're making it as user-friendly as possible, minimizing installation dependencies, try to have single scripts for training and inference, and making it relatively easy to add new AI models and data sets. This is still an ongoing process, but it's something that's guided our development. And what I think differentiates us from some of the other groups that are coming from, say, tech companies is that we bring in both AI and atmospheric science expertise. And this has led to us really being able to think through things like what input should we be using, what physical constraints should we be adding, how can we use both the AI and the physics, come up with ways to stabilize the model runs over long periods of time. And we also bring in experience on developing and deploying AI models for a variety of other use cases over many years. So I'm going to kind of jump from the overall framework into talking about first our kind of initial weather model, and then some of the more recent developments we've engaged in just the past few months as we've been building the system out and deploying it on additional use cases and from both weather and climate. So our first weather model, we start with Era 5. Unlike a lot of the other groups, we've been using hybrid sigma pressure levels, or the native Era 5 model coordinate grid, instead of interpolating to pressure only. We also basically have a kind of reduced set of state variables, so we're not predicting, say, geopotential height directly. We can infer it from from temperature and specific humidity and surface pressure. And we use 16 vertical levels that we just pick from the 137 original vertical levels out of Era 5. We have a few fields that are on a single pressure level that we use as kind of a quick diagnostic, and then we have two static forcing variables: geopotential at the surface and land sea mask, and then we use top atmosphere solar radiance to force the diurnal and seasonal cycles. Our architecture, basically, we use more or less a fancy UNet. On the encoder side, we use something called a cross-former architecture. So the X and Rex former model stands for cross-former. What this does is basically you take your whatever your grid is, and you overlay varying size patches. So we have 32 by 32 or 16 by 16 or 8 by 8, 4 by 4. You patchify your data set and then flatten those patches and kind of concatenate them. And then you run kind of attention on that. So we do a short distance attention for neighboring patches and long distance attention for much further apart patches. And this allows the model to kind of learn different scales and connections, not just in the local neighborhood, but across larger domains. And we repeat this process both at kind of very fine scales as well as much coarser scales. And then on the decoding side, we just do convolutions and include kind of both passing through convolutions from the coarse scales as well as forcing outputs from the fine scales to come up with our next time step. Another innovation we found with this is adding something called spectral normalization on our weights, which is a way to help. It's a form of regularization that stabilizes our kind of the autoregressive models and autoregressive rollouts. It was originally used for generative adversarial networks to help stabilize their training, and it turns out to be very useful in this context. So one of the things we can do with this is it means when we don't include this feature, we find that multiple architectures we tested would just go unstable numerically, and you get these black holes of expanding size that would basically destroy your state. But with this, we get rid of the black holes. We still sometimes get some artifacts from some physical inconsistencies that sometimes show up, but otherwise we usually in the form of kind of high frequency waves that start propagating in random spots. But otherwise we see much more stable rollouts, and we're able to do an hourly stable rollout up to 10 days. In terms of performance, on this chart, the blue line we have the IFS. So you see basically for the curves that go up are RMSE, and the curves that go down are the anomaly correlation coefficient. And we basically see big performance gains with all the fields, especially with specific humidity, but also with other fields. And we test multiple architectures, so a Rexform architecture, as well as we trained our own version of the Fuxi model, which is developed in China. And we basically borrowed their architecture, but made a smaller model. But unlike the original one, we're able to use one model for a 10-day rollout instead of 2, which is what they have to like switch to a second model after 5 days. And so basically we're finding like we're getting consistent improvements. Performance generally looks good. We're also, in addition to looking at individual variables, we're also looking at correlations among different variables, because one of the things that is important from a forecasting perspective is being able to do let's see how to describe it. Like you're not only interested in like individual variable performance, so you're also interested in learning the relationships between variables, because that's a key need for if you're using this kind of model for data assimilation. Because usually with data assimilation, if you update your pressure, if you get any pressure observation, you can use that to update temperature and winds if you have the right correlations. And so if we're learning, we're finding we learn those pretty well, but there are some deviations, and some models have bigger deviations than others. Depending on the variable, we see some of the deviations seem to be a bit like change sign or direction when you go between the troposphere and the stratosphere. But these deviations are still relatively small, and we're mainly getting the correlations right, just something a little off. And this is at like looking at 10 days into the forecast, so it's seeing a lot of integration. That was kind of our initial go at the modeling problems, and from that we like saw like, hey, this is possible, this works really well, it's fast. What can we do to improve it further from there? And so one of the things we're looking at is how do we impose physics conservation on the models, but do so in a way that doesn't require a lot of custom coding and a lot of like tweaking of the architecture. And so the approach we've taken is one, basically, again, we're using a more limited variable data set. Although this we're predicting pressure levels rather than sigma levels, but we've been able to do these physics conservations both with pressure and sigma level vertical coordinates. We added a bunch of cumulative diagnostics that cover different kinds of fluxes. So we predict precipitation and evaporation, radiation at the top of the atmosphere and at the surface. And then we have other forcings that help provide information about land, sea, terrain, sea ice cover, and soil type. And with all of these, we plug into the Fuxi architecture, but you could also use the Wexformer. And then after running our model, we do first a non-negative correction to get rid of negative humidity and precipitation, global dry air mass conservation, where we basically adjust some of the variables so that the total dry air mass matches that was found basically at the initial time step. We also do a global moisture budget conservation on total precipitation and evaporation by adjusting those fields, and then global total atmospheric energy by adjusting the temperature fields. And we basically adjust this so that the global total energy is in balance. This doesn't necessarily mean all the individual grid cell variables are in balance, but by preserving the total and basically just scaling everything up or down, we don't have to mess with any of the patterns, and we're not directly messing with the state very much. And then we basically do a loss and back propagate through all of these through the model, and that helps the model learn to conserve all this more effectively. We also still keep all these in place during inference to basically make sure they are always enforced. We find that to be necessary for this kind of problem. So what does it look like with and without physics conservation? Well, without, we get this, basically your total dry air mass fluctuates around pretty significantly. Whereas with the physics conservation, we were able minimize the fluctuations considerably. It's not an exact conservation because we're running at reduced precision at a 32-bit floating point rather than 64. And so we notice that has an effect on it. But if you use 64-bit floating point on a GPU, you lose a lot of the speed ups from the GPU because they're not optimized for that. And then we also run a global, also are able to fix our global moisture budget and reduce the residuals on that. And then with precipitation, we basically keep the precipitation in balance around a fixed amount rather than having the global precipitation drift over time. And so that basically helps stabilize the model quite a bit and get something that is much more performant over time. So where do we see the benefits of this? One of the areas we see is in precipitation, where we remove the light precipitation bias that's present both in the IFS and in our baseline model. So you can especially notice it over like the Sahara and Antarctica, where basically there are large areas of liquid precip still falling. So we get rid of that, but also without messing with the extremes, and that results in improvements in our basically our scores for SEEPs, which is a way to verify global precipitation, and especially at longer lead times, we're seeing our model outperform the IFS in terms of its precipitation scores. We also see improvements in other fields like 500 millibar temperature, geopotential height, and mean sea level pressure, especially at longer lead times. It seems like 96 hours is sort of the magic point where we like the baseline model starts to diverge and have higher errors and less improvement. But the system also allows us to get other fields out that you don't normally see in these AI weather models. So we have total precipitation, but also we have a kind of a indirect cloud representation through the total atmosphere net thermal radiation. And so you can kind of see the clouds sort of propagating along with the precip. And you can also see the diurnal effects of the sun also propagating through the system. We've also tested the effect of changing the vertical coordinate on our precip forecast, and we find if you combine the physics constraints with a hybrid sigma vertical coordinate, especially over land, we see improvements in basically our long range precipitation forecasts, and we get in particular better slight improvements at earlier lead times, although those improvements kind of converge with the pressure level physics at longer lead times. And both of these have a big improvement over just changing the vertical coordinates. So you need both the conservation and the vertical coordinate change to see these effects. This is especially notable in complex terrain. So this is off the coast of British Columbia for an atmospheric river case. So these are all day 5 forecasts from different models. So iMerge is our satellite-based observation that we're using as our baseline. We see some extreme precipitation over kind of Vancouver Island. If you just use pressure level physics, you don't get the extreme precip at all. With the sigma physics, we get extreme precip over. Basically, we're capturing those orographic effects more accurately, although they're a bit overdone across all the mountains. Then with only the sigma pressure, we do get some extreme values, but they're offset. So having basically the argument here is having it's not just a either or, but it's a both and to get the best performance. And that's that with a 1 degree model for reference. So that's kind of our experience at the weather scale. But we're not interested in just stopping at 10 days. We want to run much further. And so Will Chapman over in our climate and global dynamics lab has been leading the development of what we call CAMulator, which is a kind of emulator of the community atmosphere model that uses the same essential architecture as our weather Wexformer model. It still uses the Wexformer architecture, but we're added in the physical constraints and trained off of of CAM with extra variables to govern everything you'd want to have in an atmosphere model that you could couple with other parts of your system. And we're finding we can get stable rollouts for pretty much indefinitely with this framework. So what goes into it? We have surface geopotential land sea mask. We're forcing it with incoming solar radiation and sea surface temperatures. And then for prognostic variables, again, we still use a fairly small set of core variables to do that. But then we have a bunch of diagnostics that govern things like cloud cover and radiation fluxes at the surface and top of the atmosphere, as well as cloud cover at different levels. And we can basically predict that from the state. We use the Princeton mushroom architecture plus the physics conservation tuned for this particular application. And we're able to, and we train it over one CAM run on a kind of forced by SSTs over from the observed record. So it captures some of the global warming signal implicitly in that. One of the big advances we've gotten with this is it is, even with all these extra variables and extra vertical levels, it is super fast. We get 480 simulated years per day, so it's about 350 times faster than original CAM, and we can run this on one A100 GPU versus 10 CPU nodes with 128 CPUs each to get much worse throughput with the whole CAM model. Of course, we're predicting a lot fewer things than CAM does, but some caveats to this. But if you want to get the same general results, like I'll show you just how close we're getting with the speed up. So we have a 1979 to 2013 SSTs forcing both CAM and CAMulator. We have ensemble CAMulators that we're running. So we're not only capturing kind of the actual CAM run in the ensemble as a plausible member, but we also are capturing the internal variability of CAM with this. Unlike some of the other models that are out there, we're actually doing a really good job at preserving kinetic energy and potential temperature in terms of the spectra. We see a little bit of loss between CAM and CAMulator, but it's not nearly as dramatic as we've seen from other systems. And then we're also able to with the SST forcing our near surface temperatures, we're seeing kind of realistic variation around our long-term trend with that. We also have showing our basically residuals of dry air mass and moisture budget. So the black line here is if you run the model without forcing the physics, basically your dry air mass drops, and then it does eventually kind of stabilize. But you can exactly conserve it if you actually force that. And then same with the moisture budget residual, you get a much kind of a spike, and then it does sort of converge, but it still bounces around. Same with global energy budget. We basically prevent all these instabilities. Total energy tendency, we also see some big fluctuations if you don't include that those forcings. We can also so we have a model. We can look at kind of our global statistics. They look pretty good. What about our teleconnections? So we have some PNA and NAO regressions, and we're seeing that CAMulator versus CAM nearly replicates kind of both the amount of, in like the first EOF, like similar amounts of explained variance, as well as the patterns they're not identical, but they are very similar. Same with the NAO, maybe some more dramatic differences. We get like kind of like sort of two nodes rather than one node, and the kind of negative anomalies are a little bit offset, but we're largely getting very similar structure. And then with ENSO, we're seeing like in terms of precip, we're getting very similar anomalies between El Nino and La Nina events between the two. There are some differences, but it's we're capturing largely the same overall forcing. So we're confident not only that we're getting good univariate results, but that the model is also representing other feedbacks in the Earth system, or at least in the atmosphere. And then that's with basically just running over the observed record, kind of over the roughly the training period. What if we try to push our model out of distribution? What happens with that? So we've done SST forcing experiments with +2K and +4K SSTs running over the same period with both CAM and CAMulator. And what we see is that, at least with things like temperature at the lowest model level at +2 and +4, at +2 we're largely replicating the right cycle. At +4 we're underdoing a bit, but we're not like regressing back to 0 or to the original forcing or anything like that. We're just kind of underdoing it. And this is without explicitly training this. As you go basically near surface, it does pretty well with some more deviations. Once you get further in the atmosphere, so like the 200 to 850 integrated heat content, we are we're definitely seeing some effects of like not that's underdoing the amount of heat content in the total atmosphere. So there's still room for improvement with this, but just from observed forcing, we are seeing some very promising results. In terms of other SST forcings, what is this looking in terms of temperature? One of the things we see is that a lot of the broader patterns we're able to keep them, but then what we see in terms of intensity, especially at 4K, where we're running into issues is that we don't have a explicit ice representation in the model, and so it's still assuming that Antarctica has sea ice off the coast. But then in the real CAM at 4K, the sea ice is going away, and so we get these pretty big biases in terms of CAMulator. CAMulator is much colder than CAM. What's interesting is we also see that it's warmer than CAM, and basically over the Sahara and the kind of the Iran, Greenland also is notably warmer. So there's some interesting effects going on there. We're seeing a pretty consistent bias over Greenland because we don't have, again, an explicit land ice and sea ice representation. I think if we add those to the model, that may help with some of these things, and adding other static forcing variables describing land, and potentially having a land model emulator that could handle some of these processes more explicitly could help address some of these issues. So then we have basically now we have a CAMulator, we have weather models. How do we expect people to actually use these in different contexts? So we want to imagine a couple of different user stories. So one is like a graduate student, like some of y'all in the audience. What if you want to investigate the effective changes in sea surface temperature patterns on snow depth in the Andes? If you have credit, if you take our a CAMulator, you could generate ensemble forecasts for 5 years on one derecho node and a GPU node, I should say, in a day, and then apply some kind of machine learning under precipitation type algorithm that we've also developed to look at rain and snow and estimate snow depth, making various assumptions about your snow to liquid ratios. And then you can rerun the whole ensemble with different SSTs and the next day and kind of play around with that. But if you're, say, wanting to do this without credit, if you have to go grab MPass to do this kind of a bunch of forecasts, you may be spending a month just generating your data, and then another month actually calculating the p-type and doing all the analysis code. So by taking advantage of this of these emulators that give you hundreds of x speed up over or other systems, it can kind of change the kinds of experiments you can do with these systems and look at other sensitivities and get closer to analyzing your scientific results instead of having to wait on a supercomputer and get a giant allocation and deal with we still have to deal with the storage issues. That's still a problem we haven't completely solved, but there's a lot you can do just by changing just making it go faster, but still being mostly true to what you're trying to emulate. Maybe you're also a risk modeler, and you want to look at compound heat waves and the compound risk of say heat waves following tropical cyclones. With credit, if you run CAMulator, you could do do a bunch of 100-year runs and run that on a GPU. So we can even like basically, if you have different initial conditions you want to start with, you can actually run the same. You can even run like up to, we've tested up to like 50 ensemble members on one GPU, and so you basically just run them all through the same model and then get a bunch of different realizations on one GPU for one day. You don't have to do this on like derecho. You can do it on AWS node or your local cluster or wherever you're running your compute. And then you, like, while you're running it, you can then run your tropical cyclone tracker in Python, and maybe you have some heat anomaly algorithm that's looking at the diagnostics. And you find all your co-located events, save just out that information, do your analysis the next day, and then you can spend more time making plots and working on the science. If you wanted to do this with current modeling systems, you would need to request, like, put in a request for a million core hours on derecho or one of your UK systems, and then you need to run for approximately 357 compute days across 500 nodes to generate a regular CAM ensemble. And you could do that in a week, but it's a lot of, basically, it's still a lot of compute you would have to manage, and then write a bunch of parallel analytic scripts to parse through many terabytes of model output. Or you had to rely on existing, like the CESM large ensemble to do that. So that's, I think there's a lot of other use cases that might sort of grow beyond those kind of things, but the speed up and the ability to easily integrate into a whole Python system has a lot of benefits toward making new kinds of experiments possible. That said, we're not the only group that's developing an AI weather prediction framework. NVIDIA, ECMWF, and Google all have different frameworks. We are certain, like, on how some of our advantages, we try to make our minimum global times by adding other physics stability features. We're able to run at a lower time step if you want to look at things like diurnal cycles and more storm scale features, or then that's an extremely useful thing to have. We support lots of ways to train at scale. We bring in multiple data sets that you can easily integrate with the model. We had a bunch of physics constraints that we're not really seeing in other models as much just yet. And our inference time, we can generate a 10-day forecast in 40 seconds, which is even faster than the SFNO, which uses fewer variables and doesn't perform nearly as well. NemoEye and GraphCast are both on the slower side. Like NemoEye takes 150 seconds, or the AIFS, the original version, took 150 seconds to do a 10-day forecast, and GraphCast is 80 seconds. GenCast, if you want the ensemble, is a lot slower and requires a lot more compute to run. So what's next for the system? We are working on a new release coming out in less than 2 weeks. It'll have real-time rollouts initialized from GFS. We've gotten that working. We also have number accelerated vertical interpolation. So if you want to, like, calculate data on pressure levels or go between, or on uniform height levels, if you're interested in, say, renewable energy applications, that kind of stuff is important. Also bringing in updates to our physical constraints, and the CAMulator code is being merged, and we're updating our documentation and all those pieces, and then you'll be able to install this off of PyPy. So that'll be coming out very soon. And the next year, we're already starting to work on graph models, ensembles of different stochastic approaches. We have a regional model that's in the works. We're planning to retrain based on all the things we've learned from what's former V1 and our physical constraints to have a new quarter degree model that has all of these nice bells and whistles, so that you can, and we want to make that as performant as possible. And then we're also interested in building out the diagnostic capabilities so that you can have more physics-based diagnostics or AI diagnostics that you can run alongside WexFormer or CAMulator, so that you can basically do storm tracking or calculating other derived variables or applying other post-processing approaches. We have a student who's been working on, like, severe storm post-processing that's looking really promising. And we're also interested in data simulation integration, starting with kind of more existing data simulation systems where we we'll see where it goes from there. So in summary, it's, I think, opening up a lot of new possibilities for training and deploying AI atmospheric prediction models. The physics and a lot of other design decisions are going to be very important in getting a performant model that runs really fast. And the code is already open. Kind of the new release is coming, but it's like you can watch it as a procedural, the pull request, if you're really interested. We have a number of papers that are already out in the archive. They're linked on our Miles website. And if you have other questions, you can ask them now, or if anything comes up later, email me at my UCAR email address. So with that, happy to take some questions.
Okay. Do we have any questions for David? So I had a question about what you're saying about the potential application for risk modeling.
Mm-hmm.
So as far as I understand it, at the moment, part of the problem with the traditional models is that because they're very expensive to run, you can't really simulate densely in the extremes of the distribution. So for that, we're kind of reliant on asymptotic theory like extreme value distributions. Do you see this type of approach as potentially replacing that, or is it a complement to extreme value modeling?
I would say it's a complement to extreme value modeling. There's certainly, like, we want to validate this for much longer rollouts and really digging into the, like, what do the distributions of like say hurricane tracks or maybe other kinds of compound events, how do they compare with this versus a like a extreme value models or more traditional cat models. I think the advantage here is we really don't have to make nearly as many simplifying assumptions. We are kind of getting a lot, at least at this kind of synoptic and meso alpha scales, we're getting a lot of those sorts of feedbacks properly generated. We see hurricanes forming and strengthening and making landfall and weakening, and we see interactions with troughs and other things that look fairly realistic. So I think, at least from the initial stuff, I think it's promising, but we I definitely want to compare with other methods and do much more rigorous research before we say, hey, go change all your like go deploy this en masse and change all your assumptions on how you're calculating your like insurance premiums and things of that nature. So I think there's a lot of potential for it to do that and to capture things that are much harder to simulate, or like you could simulate in a climate model if you had enough time to wait. But may not be feasible in a like just computationally. We might, I think we have a chance to get there with these sorts of models.
Yeah, I was thinking you could maybe validate the extreme value theory, like apply the extreme value theory to your a subset of data you generated, and then generate a load more because it's cheap, and then see if it's really working.
Mm-hmm.
So I think we have a question online. So for risk modeling, does credit perform downscaling as well?
Currently, we're working on a regional time stepping model that will run at it's trained off of like 4 kilometer data, so it can run at 4 kilometers. So that will be kind of more of a sort of hybrid statistical dynamical downscaling. But you could also apply other downscaling methods if you have high resolution terrain and other variables to do like more of a diagnostic style downscaling. I'd say we'll have more features to come, but we've been focusing more on the 4 time step modeling rather than downscaling. I've been involved in other downscaling projects. There's certainly a lot of other groups doing downscaling. So it's we're trying to, I would say, fulfill a need that to have this kind of open system. And in terms of commercial purposes, yeah, we've released the code and the models under a permissive license. So this can be used for both research, non-commercial applications, and commercial applications. That said, we're still working on validating a lot of stuff. So before you run off and build your company around it, you might want to consult with us first.
Okay, and we have a question as well from John Marsham.
Yeah, John.
All right, it's a great talk. There's a lot there. I just wanted to check, did you show anything that showed predictions of SSTs? And if you didn't, do you see any kind of limitations in machine learning in the future from being able to predict SST evolution? Because obviously it's really important on the longer timescales.
Yeah, there are groups working on AI ocean emulators. So like there's the Samudra model from M squared lines, and I think there's other groups that are doing with regional. There's like an OceanNet regional model that can predict SSTs, and I've seen a few other papers coming out that are looking at that at the ocean problem in particular. What I would see, like where I would see that going is having either a couple, like you have one model that couples and does everything, or more likely, because of the differences in data sets, you would run a AI or physics-based ocean model to generate the SSTs and then force the atmosphere with that SST model. If you have a dually coupled system where you could take the atmospheric temperatures and winds and force the ocean model, that's actually why we plugged in like we have wind stress as an output variable, for instance, so you could take that and force it into a wave or ocean model. Longer term, we want to couple using things like the ECMWF or system modeling framework that CESM uses, but it's its own software effort to do all those pieces, and we've been focusing on the core system. But it's certainly in the roadmap. I think it's certainly possible, and expect to see interesting interactions once we get to that stage. There is, like, I think one coupled atmosphere ocean model that has actually been running out of Dale Duran's group that's been able to run out indefinitely. I think it's like a 2-degree resolution, but it is working. They're seeing realistic feedbacks and stuff. So I think there's promise in this, and a lot more work to be done.
Okay, do we have any more questions? Nope. Okay, let's thank David again.
Thank you so much, everyone.